Hello everyone, myself Dr. Shankar Singh. Welcome to my playlist Analog Communication System. In this lecture, I am going to explain about the noise. What is the noise and its type. And in the last I will take some example to clear the doubt about the some problem. So based on some noise formula, I will take the example and solve to that. Right. So let's start. What is the noise? First, let's understand. Noise is an unwanted electrical disturbance. In the first lecture, I have already explained about what is the noise. So here I am again telling you the noise is unwanted electrical signal, right? Which creates the disturbance in the communication, which gives rise to the audible or visual disturbance in the communication system. Ultimately, it creates a problem in the communication system. So when the communication is not properly happened between the transmitter and receiver end, so the noise will play the important role. So noise will get added into the channel, which will create the problem in the communication between the transmitter and receiver. It may be audible or visual disturbance. Sometimes what happen in the case of mobile communication, voice is lacking. That may be due to the noise. It may be due to the natural noise, man-made noise, or due to the internal device noise, that is called as internal source of noise. Okay, so that is actually the problem of the audible. That is again a problem of the audible during the communication in the mobile system, that is due to the noise. When we talk about the visual disturbance, when you see the TV over your setup box, through your setup box, so sometimes the environment create the problem like very heavy rain or any other things. Okay, so you are not getting any signal on your TV. That is actually visual disturbance on your TV. That is the type of problem which is creating the problem during the communication. So this is the definition of noise. Noise means unwanted electrical signal which create the problem during the communication. It may be audible or visual disturbance. So source of the noise is given here. What is the different sources of noise during the communication arises? So noise can be arise from the different types of the source. First source is the natural sources, man-made sources, and fundamental sources, that is also called as internal source of noise. So major category of the noise source is natural, man-made, and fundamental, that is also called as internal sources. Okay, let's start one by one. I will explain you each and every source of noise in the very detail. So first let us explain here. I am going to explain here the natural source of noise. Natural phenomena like electronic storm, solar flares, and radiation in the space are producing noise, known as natural source of noise. So actually natural source of noise is due to the natural action. It is not artificial, it is not man-made, it is not internal source. It is generated naturally, which may create the problem in the communication. Okay, so that is called as natural source of noise. For example, electronic storm is there, solar flares are there, radiation in the free space are there. This may create the problem in the communication. That's why it is called as natural source of noise. All these phenomena are the natural. We don't have any command over this type of the problem. So it may create anytime, anywhere, anything in the communication. Okay, it may stop pure communication, it may stop partial communication. Anything can be happen due to this natural source of noise. If I am taking the example of the noise due to the natural source, so let's divide here. Extraterrestrial noise is there. So it is further divided into two branch, that is the solar noise and cosmic noise. What is the solar noise? Sun being the very large body, and it is have the very high temperatures, which radiates a lot in the noise, a lot of noise. Okay, so sun is a very large body and which is happen at a very high temperature. It radiates the temperature in the free space. When the sun temperature is very high, then this may create the problem in the communication. Okay, so that is comes in the category of solar noise. And the second noise is the cosmic noise. It comes from the stars and it is also called as the black body noise. Right? So this is the category of natural source of noise. Extraterrestrial noise is divided into two parts: solar noise and cosmic noise. Solar noise comes from the sun and cosmic noise comes from the stars. And second part of the noise is the man-made noise. What is the man-made noise? Just you can understand here. It is generated due to the make and break process of current carrying circuit. If any circuit is there which is carrying the current, if I am making some that wire, or you can say break that wire, then noise will disturb and noise will create in the communication. Right? So I told you in the previous lecture that when one telephone line is there from exchange to your home, and sometimes the telephone line cable become faulty, so somebody will prepare that and correct that, but due to some problem that may create the spark ignition at that joint point, that may create the break process, or you can say that is the actually man-made source of noise. If proper joining of the wire is not there, so the noise may produce in the communication. Noise cannot be proper between the exchange to your phone. That is man-made noise. So if you take the example of man-made noise, you can see electrical motors, welding machines, ignition system of the automobiles, fluorescent light, switching gears. These are the example of the man-made source of noise. Right? And the third is internal source of noise. This is the very important source of noise. It is of five types. If I am divide the internal source of noise, or you can say fundamental source of noise, it is divided into the five types. First is actually called as the thermal noise. Second type is of short noise. Third is partition noise. Fourth is low frequency noise or flicker noise. And fifth is the high frequency noise. And this is also called as transit time noise. So internal source of noise is divided into five category, that is the thermal noise, short noise, partition noise, low frequency noise and high frequency noise. I will explain you each and every noise in the very detail. So what is the thermal noise, just you can understand. So actually before going to explain each and every internal source of noise, let us define what is the internal source of noise. Internal source of noise are within the electronic equipment, right? Any electronic equipment is there, when the noise within the equipment itself, that is called as internal source of noise. That may be due to the manufacturing problem, or you can say material problem. Okay, they are called as the fundamental source of noise, because they are integral part of the physical nature of the material used for making the electronics component. So variety of material like semiconductor material and other material are used to make the electronic component, electronic device. Okay, so due to the problem in the material, or you can say nature of the material, noise may create in the device, which may create the problem in the communication. That is actually called as the fundamental noise, or you can say internal source of noise. Right? So it is divided into the five part, that is thermal noise, short noise, partition noise and low frequency noise, high frequency noise. Low frequency noise is further called as flicker noise, or you can say 1/f noise, and high frequency noise is called as transit time noise. What is every different internal source of noise? I will explain you one by one. So first is the thermal source of noise. So what is the thermal noise? Just you can see the free electron within a conductor are always in the random motion. This random motion is due to the thermal energy received by them. So I am taking the example here. This is the conductor, and within this conductor free electron is there. Okay, so this free electron is randomly moved within the conductor. So what will happen due to this motion? So distribution of free electron within the conductor is not uniform. At a given instant of time, Therefore, it is a possible that more number of electron may appear at one end and other. So at a one instant of time, I am, let's say I am taking the example here at T1. This is the distribution of electron at T2. So you can see in this figure, so at the time T1 the number of electron is more at this terminal, and at time instant T2 number of electron is more at this terminal. Okay, so this free electron is moved within the this conductor freely, but when I am taking the at particular instant of time, the distribution of free electron within the conductor is not uniform. It may be very much at one end and other. Okay, so what is the problem with this distribution? Hence the average voltage resulting from this non-uniform distribution is 0. So the average voltage resulting from this non-uniform distribution is 0, but the average power is not 0. This power will be not 0, but average voltage will be 0 due to this non-uniform distribution of the free electron within the conductor. So what is that? So this power results from thermal energy. So actually this power is generated, power is not 0. So that power is what? Why this power? This power is from the thermal energy received by that free electron due to this random motion. Okay, this is called as thermal noise power. So this random motion may provide thermal noise power within the conductor, and it is defined by, or you can say it is given by Pn directly proportional to temperature and bandwidth. So Pn proportional to Tb, and proportionality constant will be there, so we can write Pn is equal to KTb, where K is the actually Boltzmann constant and its value is 1.38 into 10 to the power 23 joule per Kelvin, and B is the bandwidth of the noise spectrum in Hertz. So you must remember that the parameter of this Pn must be in the given unit. Bandwidth in Hertz, temperature of conductor must be in the degree Kelvin. Okay, joule is the K is the Boltzmann constant, which is defined in the joule per Kelvin. Okay, so this thermal noise power is given here, that is Pn is equal to KTb. K is the Boltzmann constant, T is the temperature, and B is the bandwidth. Okay, bandwidth is in Hertz, temperature in Kelvin, and K is the Boltzmann constant, that is joule per Kelvin. Now I am taking the example here, I am making the one equivalent circuit for a conductor. So one equivalent circuit is given here. Here the source voltage is Vs, and internal resistance of this source is given by Rs, that is the input resistance, and RL is the load resistance across which we are taking the output. Okay, and where we calculate the maximum power, that is PL max. Then further we convert this equivalent circuit for a conductor I am drawing here, and convert into the equivalent noise source. Then equivalent noise voltage Vs is converted into here Vn. Okay, and its value will come Vn square is equal to 4k TBR. And how actually it comes, just you can understand here. This is voltage generated equivalent circuit for the noise source. Okay, here the voltage source is there, and this the second circuit is for the current generators equivalent circuit for the noise source, in which the current source is there. In the first one, voltage source is there, that is creating the problem, and in this the current source for the noise. Okay, so from the figure one is this. Okay, from the figure 1, the maximum power is delivered to the load resistance is RL. This across this load resistance we are going to calculate the power. Okay, so maximum power across RL is what? That can be calculated by using the maximum power transfer theorem. So how to calculate? PL max is equal to V square divided by RS plus RL. This V is the actually RMS source of voltage, and it has the relation with the Vs. V is equal to Vs divided by square root 2. Okay, so we can put in the place of V as Vs divided by square root of 2. I am calculating the power across the load resistance RL. So what we can write? PL max is equal to V square divided by RS plus RL. Okay, when the maximum power will be across the RL, what will be the condition? We know that from the maximum power transfer theorem, power can be transferred across the load when source resistance will be equal to load resistance. Okay, it means when RS is equal to RL, then maximum power can be transferred across the load from source. Okay, so let's solve further. So you can write PL max is equal to Vs square by 2 after putting V is equal to Vs by square root 2 and divided by Rs plus RL. And we know that for the maximum power transfer theorem, this Rs will be equal to RL. So we can write PL max is equal to Vs square divided by 2 and multiplied by 2 Rs. So this will give the 4 Rs. Because you can calculate here Vs square by 2, Rs plus RL will be 2 Rs. So multiplication of these two will give the 4. We can find here, we will obtain here PL max is equal to Vs divided by 4 Rs. Okay, so this is the maximum power across the load resistance RL. Now applying the same logic to the conductor which is generating the noise. So I am applying the same logic for this case. This is the equivalent noise source is given here. Equivalent noise source is Vn is given here. So I am just applying the same logic for the conductor where the noise source is Vn. And now I am calculating the maximum power across the R that will give the noise power. Because the source is the noise. Source is the noisy voltage that have the Vn. The power delivered to the resistance R will give the noise power. Okay, so I am calculating here Pn. Pn is the actually thermal noise power which is across the resistance R, and this will be why this will be due to the noise voltage Vn, right? At the in the circuit it is given. So we can write Pn is equal to Vn square by 4R from this circuit. From this circuit, what we can write? Pn is equal to Vn square by 4R as we have calculated for the earlier case in the first one. Okay, and in this case where R is, this R is the resistance of the conductor and this Vn is the RMS noise voltage. This Vn is RMS noise voltage. Now we know that this thermal noise power, this Pn is what? That is the thermal noise power due to the source Vn, and we actually know that known as for the conductor case thermal noise power is given by Pn is equal to KTB. Earlier I defined you Pn is what? That is the KTB, where K is the Boltzmann constant, E is the temperature, B is the bandwidth. Earlier I told you this is the thermal noise power which is generated due to the thermal energy received by the electron. Okay, so here I am taking the example of this is the conductor. So within the conductor thermal noise power will be there. So it is equivalent to the KTB, right? So upon equating the equation number 2 and this equation, so what we can write? KTB is equal to Vn square divided by 4. So we can write here Vn square is equal to 4 KTBR. So we can write Vn is equal to square root of 4 KTBR. This is the very important relation with the for the conductor, how to calculate the thermal noise voltage. Okay, if the any conductor which have the resistance R, thermal noise voltage Vn. Okay, Vn. So what will be this Vn? This Vn will be equal to square root of 4 KTBR, where K is the Boltzmann constant, T is the temperature in Kelvin, B is the bandwidth, R is the resistance of conductor. Okay. Similarly, for the current equivalent circuit, you can calculate the RMS noise current. Earlier, I calculated the thermal noise voltage. This is the actually thermal noise voltage. You can calculate the thermal noise current for the case of current source. Okay, so similarly, you can find current source. I have already drawn here. You can see this is the current source. This In square is equal to what? That will be 4 KTBG. G is here because G is equal to 1 by R. This is the conductance. Okay, so you can calculate the in the same fashion and you will find the thermal noise current will be equal to square root of 4 KTBG, where G is equal to 1 by R. This is again a very important relation to calculate the thermal noise current. And earlier this was the thermal noise voltage. Further, the second type of the internal source of the noise is the short noise. Okay, what is the short noise? You can understand first. It is produced due to the random variation in the arrival of electron, or you can say holes, at the output electrode of an amplifying device. If any amplifying device is there, okay, so let's say I am taking the example of transistor, which may act as a amplifier. So this is the emitter, this is the base, and this is the collector. So what will happen when the random arrival, it is produced due to the random variation in the arrival of electron and holes at the output of electrode of the amplifying device. This is the output electrode. If the random variation, the arrival of electron and holes at this collector, okay, so that will actually cause the short noise, short problem, short effect. So short effect is one phenomena. So that random fluctuation in the arrival of electron and hole is called as the short effect, and due to this short effect noise will arrive, that is called as short noise, right? So short noise is why? Due to the short effect. And short effect is what? That is the random variation in the arrival of electron or holes at the output electrode of an amplifying device. Therefore, it appears as a random varying noise current superimposed on the output. Due to this phenomena, what will happen? Random varying the noise current at the output. Okay, at the output electrode, due to this random arrival of the electron and holes will cause the random variation in the noise current. That will cause the noise that is actually called as the short noise. So short noise has the uniform spectral density like the thermal noise. So this is the like thermal noise, it has the uniform spectral density. Now the exact formula for the short noise can be obtained only for the diode. We can calculate for the amplifying device, but it is the very complex. So for the diode I am writing here the what is the short noise current. Okay, for all other device the approximate equation is stated, not the exact one, because that is the complex, that is having the complexity. The mean square short noise current for the diode is given here. In square is equal to 2 times I plus 2 I naught QB ampere square. Okay, where I is the actually direct current across the junction in ampere. This is an ampere, and I naught is the reverse saturation current in the ampere. Okay, and Q is the electron charge, and B is the bandwidth. Q is the electron charge which have the value 1.6 into 10 to the power minus 19 coulomb. Okay, and B is the effective noise bandwidth in hertz. This is defined in hertz. So short noise current here In square is given by 2 times in bracket I plus 2 I naught QB. I is the direct current, I naught is the reverse saturation current, Q is the charge value, that is 1.6 into 10 to the power minus 19 coulomb, and B is the bandwidth in hertz. Okay, so for all the amplifying device the short noise is actually, we can say, this is inversely proportional to the transconductance. Transconductance means that is the GM. So the short noise will be inversely proportional to 1 by GM, and it is directly proportional to the output current I naught. If output current is I naught, so short noise current will be inversely proportional to 1 by GM, that is the transconductance, and directly proportional to I naught. So this is the approximate equation in the case of amplifying device. But in the case of diodes, we have written here the equation, that is In square is equal to 2 times I plus 2 I naught QB. Okay. Now the next internal noise is partition noise. The third type of the noise is the partition noise. What is the partition noise? You can understand here. It is generated when the current gets divided between 2 or more paths. Okay, so I am taking the example of transistor, that is the NPN transistor. Okay, so what will happen in this case? The emitter current will be equal to base current plus collector current. So current is dividing at the junction. How it is dividing? Dividing in such a fashion that I is equal to IB plus IC. So it is generated, means partition noise will be generated when the current gets divided between the 2 or more paths. Okay, so here between the three paths the current is divided. Two incoming current at the junction, that is IB and IC, and one is the current going towards the emitter, that is IE. So IE is equal to IB plus IC. So current is divided at the junction in this case, right? So it is generated due to the random fluctuation in the division of current. Due to this random fluctuation, due to this current division will cause the partition noise. Therefore the partition noise in the case of transistor will be higher than the diode. This is the case of the diode. In the diode there are no any division of the current, there are no any junction actually, so current division will not be there, so there will be no any fluctuation in the current division. But in the case of transistor, current division is there. Therefore due to this current division, random fluctuation of the partition of the current may happen. Due to this, partition noise will come into picture. Therefore the higher partition noise will be in the case of transistor than the diode. Okay, current division is happening at the junction, therefore the short noise would be higher than the diode. Not short noise, this is the partition noise. Okay, partition noise would be higher than the diode in the case of transistor. Now the fourth types of the internal source of noise is low frequency or flicker noise. This is also called as 1/f noise. Okay, so what is the low frequency noise or flicker noise? Just you can understand first. Flicker noise will appear at the frequency below a few kilohertz. First you must remember that it is happening at the frequency which must be less than few kilohertz. Okay, if frequency is high, then low frequency noise will not happen there, then the other type of the noise will come, that is the high frequency noise will be there. Okay, later on I will explain you high frequency noise. It is sometimes also called as the 1/f noise, that I already told you. In the semiconductor device, flicker noise is generated due to the fluctuation in carrier density. Okay, at the lower frequency what will happen, the carrier density in the semiconductor devices is fluctuating, is changing. Due to this carrier density changing, this will cause the fluctuation in the conductivity of material. Okay, due to this carrier density fluctuation, conductivity of the material may change, and this will produce a fluctuating voltage. If carrier density is changing, it means conductivity is changing. Conductivity is changing, it means voltage will be fluctuating. Okay, voltage drop will be changing when the direct current flows through the device, and this fluctuating voltage is actually called as the flicker noise. So for the semiconductor device, you can understand here, carrier density is fluctuating. Due to this carrier density fluctuation, conductivity is fluctuating. Due to this, voltage drop is fluctuating. So this voltage drop at the output of the device may cause the problem, may cause the error. That is actually called as the low frequency noise. This carrier density fluctuation is happening when the frequency is less than few kilohertz. That's why it is called as the low frequency noise, or you can say flicker noise, right? So at the low frequency what is happening, carrier density is fluctuating, due to this conductivity is fluctuating, and due to this voltage drop is across the output will be fluctuating. That will cause the error, or you can say noise in the communication, that is called as the low frequency noise, which happened, carrier density fluctuation may happen at frequency less than few kilohertz, or you can say flicker noise is called this. And the fifth type of noise is, that is the last type of the internal source of noise, that is called as the high frequency noise or the transit time noise. What is the high frequency noise? You must understand here. If the this high frequency noise is actually the phenomena is happening in the amplifying device, that is the transit time effect. Okay, transit time effect is what they, you must understand that, and based on that transit time effect, the high frequency, or you can say transit time noise, may take place. So you can understand what is transit time actually, this transit time effect. If the time taken by the electron to travel from the emitter to the collector of a transistor becomes comparable to the period of the signal which is going to amplified, then transit time effect takes place. Now you can understand here, this is the amplifying device. I am taking here example of PNP. Okay, so you can say this is the symbol of the PNP, and I am taking the example here that this is the current which is flowing from emitter to collector, and time taken T2. This time T2 time is taken by the electron to travel from emitter to collector. This T2 is the time which is taken by the electron, which is taking the time T2 to reach from emitter to collector. Okay, when this T2 time is what? T2 time is time taken by electron to reach from emitter to collector. When this T2 time is equal, or you can say comparable to the signal which is going to be amplified, I am applying this is at the input signal, and this is the sinusoidal signal. I am taking the its time period at as T1. This is the input signal which is going to be amplified by this amplifying device, and its time period is T1. Okay, I am saying here when T1 is comparable to T2, then transit time effect take place. Okay, so when T1 is comparable to T2, then transit time effect takes place. And what is T1? T1 is the time which is taken by the electron to travel from emitter to collector, and T2 is what? T2 is the time taken by electron to travel from emitter to collector, and T1 is the time of the T1 is the time period of the signal which is going to be amplified by the amplifying device. So same is written here. If the time taken by the electron to travel from emitter to collector of a transistor becomes comparable, let's say I am taking here become comparable, become equivalent to the period of signal which is being amplified. Period of the signal is T1. Then the transit time effect may take place. When T2 is comparable to T1, T2 is the time taken by electron to reach from emitter to collector, and T1 is the time period of the signal which is going to be amplified. If both are the comparable, then transit time effect take place. Okay, and this phenomena may happen at the very high frequency, above few megahertz, and due to this some carrier may diffuse due to the back to the emitter. Due to this reason, due to this problem, when T1 is comparable to T2, due to this problem the carrier may diffuse back to the emitter. Okay, and this may is called minute current induced in the input of the device by the random fluctuation in the output current. And due to this carrier diffusion, very minute current will be induced in the input, and this minute current induction in the input may cause the random fluctuation in the output current. Okay, this is important, and this will create the random noise at the very high frequency. This is called the high frequency or transit time noise. So basically high frequency or transit time noise is actually occurs at a very high frequency, maybe above few megahertz, and due to this is happening due to the transit time noise. When transit time effect takes place in the amplifying device, what will happen? Some carrier may diffuse back to the emitter, and due to this diffusion of the carrier in the emitter, very minute current may induced at the input, and due to this minute current induction may cause the fluctuation of current at the output. Okay, fluctuation of the current at the output, this may cause the problem that is actually called as the high frequency or transit time noise. This is all about the different types of the noise and what is the noise. I am taking one example to clear the one equation that I have derived you, thermal noise voltage. Based on this formula I am going to take one example and solve that. So example is here, an amplifier has the bandwidth of 4 megahertz with 10 kilo ohm at the input resistance. Calculate the RMS noise voltage at the input of this amplifier if the room temperature is 25 degrees Celsius. So this is the problem. In the problem, first let us identify what is the given. Okay, so its bandwidth is given, B is the 4 megahertz. So I told you to calculate the noise RMS noise voltage, first you have to write the formula. This is the equation, that is the Vn is equal to 4 kt square root of 4 ktBr. K is the Boltzmann constant which is known. T is the temperature. I told you this T is the temperature in degree Kelvin, and in the equation it is given T is the 25 degrees Celsius. It is in degrees Celsius, so must convert into the degree Kelvin. So you will find 273 plus 25 degree Kelvin, you will find 298 Kelvin, right? And B is the bandwidth, is given 4 megahertz. So you must convert this into the hertz, that is 4 into 10 to the power 6 hertz. And resistance is given, input resistance is the 4 kilo ohm. Input resistance is there, and you need to calculate the input RMS noise voltage. So noise voltage formula is there, Vn is equal to square root of 4 kT Br. Every value is known, that is B, T and R is known. You can, and K is the Boltzmann constant, that is actually given 1.38 into 10 to the power minus 23 joule per Kelvin. So you can put the value of every parameter Kb, RT in this equation. You can find the thermal RMS noise voltage, and it comes to be 25.65 microvolt, right? So this is one example based on the RMS noise voltage equation that we have already derived in the lecture. Thank you. This is all about the noise. We will discuss further. We will discuss other part of the noise for the amplifier, SNR, noise factor calculation for the amplifier, and cascade case, that we all discuss in the for the lecture of the noise. Thank you. Thank you for watching this video.